Okay, so, the last couple of years I was involved in a big project for the Norwegian government to basically replace their old, infrastructure with something token-based, basically OpenID Connect and OAuth and so on. So as part of that project, I created this internal training to raise awareness of, security challenges or, security features or security, problems you might run into. So what this slide deck is basically like a subset of that training. So I picked out like some more common problems and maybe some less common problems to basically raise the awareness with you as well. And then hopefully encourage you afterwards to go start reading these documents, because obviously there is much, much more to learn about this than what I can tell you in 60 minutes. So, but I have to warn you, right? When you start digging into this matter, then you're gonna have to read things like this, right? It's a Korea font, right? You know that's where the fun stops here. It's all very serious. Luckily, they have a PDF version for you, right? So when you click that, you really hope, give me something nicer. Apparently, the internet doesn't work. So I can't show you the PDF version, apparently. But the news is, the spoiler alert would be, they use the same font. Okay, so it doesn't really help. Yeah, and that all goes back basically, that whole procedure of RFC must be written in text files and so on. That all goes back basically, the IETF is the company that specified the internet in the first place. So basically all of these documents must really be backwards compatible to the very first browser you ever had. Did you know the very first browser you ever had? It's called Lynx, right? It's a text-based browser. You can see it also doesn't work. Because there is no internet. But if you would open the document in that browser, it would look exactly the same as in Chrome. So that's 30 years of backwards compatibility. And they even had dark mode back in the day, so I think, that's pretty good. Luckily for the rest of the talk, I don't need internet. Okay, so my name is Dominick, and I'm a security consultant, and I also work on this thing called Identity Server, which is an open source implementation of OpenID Connect and OAuth. So I get to implement these protocols because, that all started as a hobby project, really, because I thought, you can only really claim you know how the protocols work when you implement them yourself, and that's what I did. Oh yeah, and maybe the other important thing is if you want to have the slides, I downloaded them to this thing called speakerdeck.com/leastprivilege, and then you can get the slides from there, and many other slides. Okay, so the rough agenda is I want to give you a little bit of an overview where to go to if you're looking for security guidance for these protocols. Then I want to, as I said, pick out some concrete issues and solutions, and then in the end we're going to talk about what's going to happen with OAuth in the future. So, but first give you some context. Basically, web-based authentication protocols, the way we know them today, all had their start in 2005. And the very first protocol that really, invented this pattern of, you have a browser, you send the user somewhere, that something sends you something back, and that's the authentication or the token exchange, was called SAML2P, right? It's an old protocol, as you can say, it's like 15 years old. But this was only an authentication protocol because it didn't solve anything like access to APIs or delegating identity to APIs. You know what? Because APIs didn't exist by the time. Then the first protocol that actually took on this problem was called OAuth 1.0. Again, that's a long time ago. It made some assumptions that are probably not true anymore today. It involved some pretty heavy crypto. It was very complicated to use for many people. So the IETF started working on this thing called OAuth 2.0 in 2012, which was a simplification of the old OAuth 1.0 protocol. And part of that simplification was basically less crypto, simplified flows, but to be honest, also less security if you look at the security properties between 1.0 and 2.0. Basically because they invented this thing called bearer tokens, where basically, if you have the token, you can talk to an API without cryptographic binding to the client that requested the token in the first place. So To be honest, and maybe some of you have followed the drama around that the spec author of OAuth 2.0, he was so upset with the IETF, taking features and features and features away to make it more easy to use, that half a year before the spec was done, he just left and made this really popular talk on the internet. You can search for it by putting the word OAuth and some of your favorite swear words in one sentence, and you're going to find it. But part of that legacy from him is that he demanded that there must be a threat model, right? Because you can, even if you implement the spec word by word, you can implement it in an insecure way. So there must be an additional document on top that basically looks at all of the security properties, looks at all of the attack scenarios that you could think of, and tell people how to fix them. But obviously, since this document was written at the same time as the protocol itself, there was no experience yet. How will people use the protocol? How will people attack the protocol, right? So the threat model is, if you think the OAuth spec is boring, that threat model is not much more exciting, to be honest, yeah? Because as I said, they didn't really know how that thing will be broken in the future, so there's no actionable guidance here, really. It's just basically this could go wrong, and this could go wrong, and this could go wrong, and you have to fix it somehow. Okay, so then, many other protocols came down the line. Actually, someone recently just counted the pages of all of the documents, of all of the specs, and realized it's double the size, double the number of pages than War and Peace. Okay, so which you then decide which one is more exciting to read. And now we saw OAuth being used in places where where in 2012 nobody anticipated it going, like financial industry, healthcare sector, high value scenarios. And guess what? As more high value the scenarios get, the more creative attackers get to find the problems, right? So there was like a demand of giving us something better than just a raw threat model. So they started coming up with what they called BCPs. And BCP stands for Best Current Practice, okay? And it's good that the word current is in there, because obviously as older as the document gets, the current is, it's less current, right? Still, they're all, pretty newish. And the idea of that BCP was to give you, as a developer, real actionable guidance. Like, if you're doing this, then you wanted to implement it exactly like this, because that's the recommendation, okay? So that's the very first BCP that came out was the one for native apps. That's been released in 2017. And very soon, there will be a couple of new BCPs. One is called the OAuth 2 Security Topics, which is more like a general thing that applies to all applications. And the one that many, many people have been waiting for is called OAuth 2 for browser-based applications, for example, because as we know, that's the most problematic type of client to secure. And basically what this talk is about is to give you an overview of these BCPs, how they hang together. And as I said, hopefully encourage you to read them, because, as I said, there's more to learn. So basically we have the threat model, like the mother of all BCPs, if you like. We have the OAuth 2 Security Best Current Practice, and on top we have the very specific ones if you're writing native apps or browser-based applications. And the one thing they sneaked in recently is two more. One is about using JSON Web Tokens with OAuth, because in the beginning, OAuth did not specify a concrete token format. They just said, use a token, right? But it's very common these days to use JSON Web Tokens for this, so that's talking about this. And yeah, these two specs kind of go hand in hand together. Okay, so how does an OAuth or OpenID Connect-based system look like? Something like this, right? We have front ends, we have back ends, we have back ends for back ends. Wherever an arrow goes to, there needs to be some authentication, right? So it turns out OpenID Connect is the less critical problem here, because it's not giving you access to something. It's only about representing identity. But whenever an arrow arrives at a web API, right, that is basically where potentially there are access tokens used. If they get stolen or somehow misused, then you can access resources, maybe not legitimately. So, but if you strip down this picture, it really always looks like this, right? Every OAuth-based system looks like this. You have a client, which is the application. You have a resource owner, which I typically call the user. You have a resource server, which is typically an API. and you have this thing called the authorization server, which is the thing that issues tokens to the client, I should be very specific, to access the resource, okay? So if you think about the security of such a system, the first thing you should probably think about is, who is going to attack it, or what kind of attacker can we expect? And you know what? Excuse me, I found the cheesiest symbol for an attacker on the internet, so I think that's how they look like. I've never met one, but I think that's how they look like. So the very first type of attack you should think about is basically if your infrastructure is compromised, right? Maybe you're not using TLS, which would be a very big failure. Or maybe you have TLS and it's compromised somehow, reverse proxies, root certificates, whatever. Or maybe even worse, your DNS infrastructure is compromised. And to be honest with you, that's pretty much game over, right? That is something as developers that we can't fix. That has to be done at the infrastructure level. The next one that we probably can't fix as developers is if the endpoints are being compromised. I mean, you have to ask yourself, okay, why are they being compromised? Somebody wrote bad code. With this attack model, the reason they are compromised is not because of the protocols. That's the idea, right? Somebody found some other vulnerability on the server or something. They could compromise the API, they could compromise the token service, or maybe the client. Yeah? Again, that's not really what we want to talk about today. A very interesting attack model, which is, in my opinion, like the battleground of the future, is basically if attackers can register additional infrastructure. Yeah? So maybe they can bring up rogue clients or rogue APIs or rogue authorization servers into the system. And even worse, maybe they can register the rogue client with the legitimate authorization server, or have the legitimate client talk to the rogue authorization server. These kinds of combinations where still the protocol might be completely spec compliant, but you're now hitting a scenario that you haven't thought about, and this might confuse you. Yeah? And that is what we see these days with very targeted attacks. Yeah? When somebody specifically targets a certain company, that is, that's where many things go on. But sadly enough, like the 80% of all the vulnerabilities are just implementation mistakes, right? Basically, the idea is that an attacker can read but not modify the contents of the authorization request or response. And that might be because we have open redirectors in our code. Yeah? We are leaking data, yeah? Maybe in log files, maybe in the browser history, maybe in proxies. Maybe you have something on the phone that intercepts the callbacks between applications and so on. That is by far the most common problem we see. And the good news is they are all just programming errors, and we can fix them. Okay? Good. So, these BCPs have been around for a while, and no one really took too much attention, unless one very respected colleague of mine, Thorsten Wollerstedt, wrote a blog post. He said, you should stop using the OAuth implicit grant. And he made it very clear by scaring people, saying, if you don't, your health records might be leaked, or someone is initiating payment from your bank account. Yeah? And you can only imagine what happened next day, right? I got emails and phone calls from companies and customers saying, hey, have you read this blog post? There's a new vulnerability in OAuth. And last week, you recommended us using the OAuth implicit flow. Are you aware of that? And I had to do a lot of explaining, saying that this is not a new vulnerability. Right from the start, if you would have read the threat model of OAuth, it says the implicit flow is a simplified model made for simplified clients, which were called by the time JavaScript clients, right? And it's error-prone. You can protect against the weaknesses of the implicit flow, but you have to write code for that, and you have to understand those weaknesses. Yeah. So long story short, this blog post started the whole thing, and now the idea is that the implicit flow will be deprecated. Okay. Just to recap very quickly, what's the implicit flow? It's basically, as I said, a simplified version of OAuth that was built for browsers that did not support cross-origin AJAX calls. Right? Because in 2012, we didn't have cores by the time, so we couldn't do cross-origin AJAX calls, so they sent around the tokens on the URL. Okay? That was the only thing that was working. As you can imagine, that this is error-prone. This can leak data if you don't protect against it. But now, in 2020, We do have cross-origin AJAX calls, and there's no need anymore to use this simplified version of it, so don't use it anymore, okay? Don't use it. While we are, that's the summary of the reasons I just told you. It's error-prone. While we are at deprecating flows, the next flow that has been deprecated is the so-called password grant. The password grant is this approach where you collect the user's credentials in the front end, then send the credentials to the server, and then you get a token back. The real name is the resource owner password grant, as they call it. This one is also outdated for a couple of reasons, right? I mean, the more you educate your users to type in passwords in different places, research shows the more they are prone for falling for phishing attacks, for example, because they just have to type in the password so often, then we don't think about it anymore, right? But if you only have this one place that you ask for passwords and that is not happening that frequently, then maybe you think about, why do I have to type in my password here? Maybe that's not a legitimate place to do that, yeah? Also, that flow is not compatible with any of the modern authentication techniques like FIDO and two-factor authentication and federation and so on. So yeah, stop using that. The nice thing about deprecating flows that were maybe useful 8 years ago but are not that useful anymore today is it drastically simplifies an OAuth-based system, right? So 1 year ago, if you would have asked me, which flow do I have to use for an application type, that would kind of be like your decision matrix, right? But now, with deprecation of all of these flows, actually, it becomes very easy. Okay? So the consensus is that we really only need 2 flows, because we really only write 2 types of applications. One is a non-interactive application, which is just machine-to-machine communication. We have a flow for that called the client credential flow. And the other one is an interactive application, basically meaning a user is involved, sits in front of a computer. For all of these types of scenarios, we have this thing called the authorization code flow, which has been around for a very long time. Guess what? The authorization code flow on its own is vulnerable to something, which I'll show you in a second. That's why there is a thing on top called PKCE, as the cool kids call it, which stands for Proof Key for Code Exchange, and I'm going to show you in a second how that works. Okay, so let's start with the machine-to-machine scenario, because that's the simpler one to understand. It's very simple. You have a client, you have the token service, you have an API. The client authenticates with the token service, by using client ID in secret, asks for access to a resource, which is typically an API. And if that is all legit, he gets back an access token and then uses that access token to call the API, right? That's as easy as it is. The first thing I want to put your attention to is client secrets, right? So again, in OAuth, client secret is an abstraction. It says the client uses some sort of secret to authenticate with the server. And obviously, the most simplest secret that at least many people think is what they call a shared secret, right? So basically, the client has a value, the server has a value, the client sends it over the wire, right? And if they match, the client is who he claims to be. Obviously, a shared secret is not really a secret, right? Because you shared it, but that's another story, I guess. But shared secrets only look easy on the outside. Once you build a real system with shared secrets, right, configuration management is hard. You have to think about key rotation because maybe you don't want to keep the same secret for all the time. How do you store them? How do you deal with them at development time? How do you make sure they don't end up in your GitHub account, right? All these things make shared secrets harder to use. If you have to use them, make sure they have a high entropy, like GUIDs, for example, random strings. I mean, these are, in essence, they are passwords for machines, right? Machines don't need easy-to-remember passwords. They can use hard-to-remember passwords. Never ever store them in clear text on your server. You always use non-reversible encryption, or also called hashing, so that if somebody actually compromises your server database, they don't get like a list of all of your client secrets. That should not happen. Since they are high entropy, you don't have to provide things like stretching algorithms, right? You only do that for passwords for humans because they are typically bad. If you have the luxury of moving away from that, go to asymmetric keys, right? Public-private key pairs where the client has the private key, the server has the public key. The server does not need to store any secret at all because public keys are not secret. The client creates some data, typically a JSON Web Token, signs that token with the private key, sends the JSON Web Token over the wire. No secret goes over the wire, right? Only the signed artifact, so to speak. So that's much better. Yeah. Again, if someone has access to your network, for example, they won't see those secrets. Yeah. And the most common ways of doing that today is the signed JWTs, JSON Web Token, as I just said, or using mutual TLS. Yeah. So mutual TLS has kind of like a renaissance the last years. It was really hard to deploy, when people think, oh yeah, CAs and PKI and so on. This has all gotten much, much easier these days. So, maybe you want to reconsider mutual TLS. The nice thing about mutual TLS is it provides us with a mechanism to bind the token to the client, right? So I said in the beginning, bearer tokens are a simplified version of a token where whoever has the token, like it's like money you find on the street, right? If I find some money, I can use it. That's a bearer token, whereas a credit card is more like bound to the owner with a picture or a signature or a pin, maybe, right? Same analogy. If you're using mutual TLS, that's really powerful because when the client asks for a token using the mutual TLS connection, the server can read the thumbprint of the client certificate, can embed the value of that thumbprint into the access token. And when then the client opens the connection to the API, he will use the same client certificate. So what the API can do is read the thumbprint from the TLS connection, compare the value in the token, and only if they match, the client has proven that he was the client that asked for the token in the first place. And if an attacker would be able to steal that token, leaking, whatever, he would not have that private key, so he couldn't use the token, right? So that's the way to go. Okay, talking about JSON Web Tokens, yeah? They've become massively popular, right? So as I said, when OAuth was specified, JSON Web Tokens didn't even exist, right? But over the last 5 years or so, they became widely available. JSON is the, data format of choice, I guess. JSON Web Token libraries are available everywhere. So people started using JSON Web Tokens all over the place, right? In OpenID Connect, we have identity tokens, we have access tokens in OAuth, we have logout tokens, we have security events, and then people come up with all kinds of, basically the nice thing about JSON Web Tokens is it's a way to protect a JSON object. So if you want to express anything as a JSON object but need integrity protection and authenticity, JSON Web Tokens are the way to go. That's a very typical JSON Web Token, right? It has a header, a payload, and so on. They're kind of like they're a victim of their own popularity, kind of, yeah? Because that's from the OpenID Connect spec, yeah? They use a JSON Web Token to send as a logout token. So these are the validation steps you have to do, yeah? So let's have a look. Validate the signature, okay, makes sense. Validate the token contains a subclaim and SID claim, okay, makes sense. Verify that the token does not contain a nonce claim. So that's weird, right? So the reason why they have that in there is because if that token would contain a nonce claim, it would be indistinguishable from an identity token. So somebody could send an identity token to the logout endpoint and do a logout even if he doesn't have a logout token, right? So, and the problem with that is that they all look pretty much the same, right? So if you're using JSON Web Tokens, then you should start using what they call typed JSON Web Tokens, yeah? So you see the type claim or value you see at the top. Normally, this just says JWT, right? But the new spec says if this token is an access token, call it AT plus JWT. And that is roughly around the same idea as content types or hypermedia types in the web. So whenever you come up with a token or a thing that you want to represent as a JSON Web Token, come up with a type so that the recipient can actually check that value and make sure, hey, this is really what I'm expecting and not something that is also a JSON Web Token and looks just very similar to what I'm expecting, okay? So starting with the latest version of Identity Server, for example, all of our access tokens look like this. They have the AT plus JWT on top, and I would encourage you doing the same if you have your own tokens. Okay, let's switch our attention to interactive applications, which are much easier to attack because they are more complicated. So if the application is interactive, there will be always like a two-part process, right? One is the the interactive part that's happening in the browser, where a user can see some sort of UI, and then the non-interactive part where on the back channel you're getting the tokens. Now, browsers are great, right? Because they can show UI and they follow redirects, right? But browsers are very problematic. Why? Well, because they show UI and they follow redirects. Yeah, sometimes to the wrong place. Yeah, and that's exactly the problem here. But in a nutshell, the way this works is you open a front channel connection via the browser. That's the authorized request that goes to the token server. The token server shows the UI and everything that's needed. Then when that is done, the token service returns the so-called authorization code back to the client application. Then the client application opens the back channel communication to turn that code into tokens. Okay? So the client sends the code, the secret, and so on, and then ultimately gets back his access tokens. Yeah, that's the way this flow works. Now, the spec says, you can imagine that this callback here, coming from the server back here, is pretty much sensitive, right? Because that delivers the artifact back to your client application. And the spec says very, very clearly, you have to whitelist these, what they call redirect URIs. And when the client asks for that or sends you that URI, you have to do an exact string matching between what you have registered in your database and what the client wants. And if they don't match, don't accept it. Okay? That's what the spec says, very clear. Yeah? Guess what people do? Is that really necessary? Can't we make it more, more flexible? For example, and these are two things I saw in real life, yeah? For example, have the redirect URI being star@myapp.com. So we can use any subdomain in that DNS namespace, right? Why would that be problematic? Well, generally speaking, right, the more flexibility you allow, the bigger your attack surface gets, where tokens or codes can be delivered to where you have an implementation flaw. If you only have this one endpoint that has only one purpose in life, is handling the callback, then you can check that code much better than having any endpoint on any subdomain. Okay? That actually happened last year to EA, Electronic Arts. So what they did was, some EA developer went to Azure, created a website that was called 123@azurewebsites.net, right? Then this was done. It was their new billing site. So then at EA, someone made a DNS entry to point billing.ea.com to 123@azurewebsites.net, right? That's what they call custom domains or custom host names, I think, yeah? All is good. Now, after a year, they decided to remove the billing website and move it somewhere else, so they shut down the Azure website, but no one removed the DNS entry. So now there was a DNS entry hanging there that points to a non-existent website. You can query the DNS server, and all they had to do was register 123@azurewebsites.net, which was still free by the time, and then you can run code under the EA domain, right? That's called subdomain takeover. It sounds funny, but it's pretty effective. Yes, so don't do that. Yeah. The other thing I've seen in real life is it's somesite.com/star, okay? We fixed the DNS name, but any page on that server will do. That exactly happened to actually GitHub and Facebook and some other big companies. So basically, some pretty smart guy found that out. He basically sent out emails pointing to a URL on that site. Let's imagine it's facebook.com/myfacebookpage. Okay, so he sent out his emails, people were clicking it, they came to Facebook, they probably were logged in already, so they didn't see the login page, it just sent the code directly to that callback URL. It was this attacker's page, and guess what he did on that page? He posted a picture that came from a server that he controls. Okay, so now the browser arrives at the page, he loads the images, he goes out to evil.com. What is the browser sending? A referrer header, right? And on that referrer header is the original URL, which has the code, and now all the guy had to do is look at his log files of his web server, and he got all of the codes that were produced as part of the authentication process. That's pretty cool, right? Yeah, you have to give him respect for that, I think. Now you say, why is this dangerous, right? Didn't you just say I need to have a client secret to be able to turn that code back into a token? Yeah, do you? There's another attack, which is called authorization code injection. So the idea is, yes, you are right, that the attacker himself cannot turn a code into a token because he's missing the client secret. But what if he now has harvested those codes, okay? And now he goes to the legitimate website, starts the authentication process, right? And on the way back, he injects the stolen code. What will the client do? Well, he will happily take that stolen code, use his client ID and secret, and turn it into tokens, right? And now I'm logged in as the victim. Does it make sense? Yeah, that's also pretty clever. This attack became published after the initial OAuth spec, so the authorization code flow has no protection against this. Yeah, so they have added an additional thing, as I said, called proof key for code exchange, or PKCE. And basically, it's a simple extension to the code flow which solves the problem. So the idea is the client, before he starts the authorization request, he creates a random number. That's a secret that only the client knows. Yeah, it's a random number. And then he hashes that random number. So the random number is called the code verifier. The hashed version is called the code challenge. So now he's sending the hashed version of that number to the authorized request. Okay? So the code comes back, right? And then on the back channel, he's sending the clear text version of the random number. So now the server has both the hashed version and the clear text version, so he hashes the clear text version. If the hashes match, the client has proven that he is the same client on the front channel as he is on the back channel. Okay? So now, if I would now come with my stolen code, that stolen code would have a different code challenge associated with it than the one I'm going to generate. They will not match, so the server will reject the request. Okay? So you have to use that if you're using authorization code flow, because that's the only way to fix the problem. Well, that's the most common way to fix the problem. Let's put it this way. Okay? So that's PKCE. So, as a summary, yeah? Always do exact matching of URLs. Never allow any flexibility. Don't think you are clever because you can use regular expressions. Okay? We all know, we all failed with that at some point in our career, right? where we thought, I can master them. Beware of open redirectors. Don't build pages that somehow forward traffic to another thing based on input, right? That's called an open redirector that might leak your data. Always use PKCE, always use content security policy. Immediately invalidate authorization codes after they've been used, make them one-time only tokens. And you know what? A very simple and effective thing is use referrer policies to make sure that your browser doesn't send referrer headers, right? That's just a simple fix that could have saved Facebook, of course. Okay. Now let's look at something which is much more advanced than I just showed you, okay? That blew my mind the very first time I saw it, and I had to read it like 5 times to understand it. It's called a mix-up attack, yeah? And the idea of that mix-up attack is that your client application trusts more than one external provider, okay? That might be the client itself, that might be your federation gateway you're running, okay? So let's say you allow registration of providers. Maybe you're running a software as a service product and the customer can self-register their own authentication system because they want to get single sign-on, right? So now you have multiple things here and maybe one of them is not so trusted as the other, yeah? So they call it the attacker authorization server and the honest authorization server, okay? So this very first variant of the mix-up attack is, has some assumptions, but it basically works like this. You know, the user clicks the link, he wants to log in with the honest STS. Now the attacker somehow has access to the network and he can on the fly change that to log in with the attacker STS, okay? So now the client will say, okay, he clicked the attacker STS link and then we'll send him back a redirect back to the attacker STS. On the way back, the attacker switches back that thing to do a redirect to the honest STS. Okay, is it already hurting? Yeah, I hope so, yeah. Now, the browser will do a redirect to the honest STS, will authenticate, he will get back a code, the code will travel back to the client. Where does the client now think he has to send his client ID in secret to? To the attacker STS, okay? And now the attacker STS can just use the code and the secret and so on to get a token, yeah? Now you might say, that means he has network access, right? And if he has network access, maybe then this is not my biggest problem. And yeah, I agree, partially. The next variant of that requires no network access, okay? It's a little bit different. So in this case, imagine the attacker has registered an STS, which looks like something that somebody wants to use, yeah? So they click the wrong button in the UI for the attacker STS, right? So the redirect goes to the attacker STS. Okay, that looks good. Now the attacker STS turns around, changes his client ID and redirect URI and everything, and forwards the call to the honest STS. So now the user sees the real login page of the real thing he thought he's talking to. So now the honest STS comes back to the client. And where does the client send the client ID and secret to? To the attacker STS. Okay? So yes, that is nothing made up, that really happened, okay? The good news is, yeah, if you're using a good framework, okay, you're probably secure already. But I've reviewed so many hand-rolled OAuth implementations in my life that definitely were not secure against this attack. But basically, the fix is pretty simple. The AS needs to always remember where he's going to. He needs to have AS-specific callback URLs that only can process this specific AS and then make sure they match, okay? So if you're using ASP.NET Core, for example, they have a built-in countermeasure, and to be honest, this was built even before the attack was known, so maybe it's a bit like secure by accident, maybe not, maybe someone was really forth-looking. That's even in Katana already, yeah? So it's actually around for a long time. The way this works in ASP.NET Core is that each external provider must have a unique name and a unique callback URL, okay? So when they now do the authorize request out to the provider, they basically create the challenge, then they create a correlation ID, which is a random number, and then they encrypt and sign that correlation ID on the state parameter, so it basically round trips back and forth, and then they create a cookie which is called correlation.authorization server name.correlation ID, okay? So now the callback comes back from that external system, so basically it's on the AS1 specific callback. It still has the correlation ID on the state, so they unprotect that string, right? They get the correlation ID, and then they make sure there is a cookie that has exactly this name. And if this cookie doesn't exist, you know that the initiation of the request and the response were for different authorization servers. Okay, and then they're going to just throw an exception, something like correlation failed. You probably all have seen that error in ASP.NET Core, correlation failed. Yeah, that's what you get. So yeah, that's what you would need to do if you're building your own little framework, and as I said, it's built into ASP.NET Core. Okay, let's switch gears a little bit to public clients. You know, public clients are clients in OAuth speak which are not on a server, which can't store a secret. They don't have a secret, right? They are deployed to a phone or to a browser. It's JavaScript, basically, yeah? In other words, you can't authenticate the client. You can't rely on the client secret protection for your authorization codes, and so on and so forth, yeah? And that would be typically, as I said, native apps or browser-based apps. So the first anti-pattern is this, right? Native login dialogues. I know some native developers have this urge to create native login dialogues. Don't do it. If you don't trust my advice, then tell everyone this is using a deprecated flow. It's using the password flow, right? Which I just deprecated 20 minutes ago. So don't use it for the reasons I mentioned earlier, okay? Obviously, the recommended flow for native apps is because you're not in the browser, you open a browser, right? It's that easy. So that browser goes to your normal login page with your, all of your code, your logging and auditing and your federation and two-factor and whatever you have, which is, it's basically, you're making sure your authentication-related code is in one place and not in 5 apps spread around, yeah? And you can make that even better by using the so-called system browser, right? So many UI frameworks have the concept of a web view, which is basically a browser inside your application without the Chrome around, yeah? Don't do that, yeah? It's bad. People can't see where they are. People cannot inspect the certificate if they really want to. maybe password managers won't work, but the real reason why you want to use the system browser is because this browser shares the cookie container with all of your other authentication state, right? So if you're already logged in to, let's say, Google, then you get single sign-on with Google inside the native app without having to type in the password again because the cookies are still there, right? And as we know, the less often you have to type a password, the better from a security point of view, okay? So yes, that's the recommended flow for native apps. They're using exactly the same flow I just shown you, which is authorization code flow with PKCE. Now you might ask yourself, no client secret. The code is even more vulnerable here. And again, that's what PKCE saves us from, right? Because even if the client does not have a static secret, which is no secret anyways, right? It has a per request secret, right? The code challenge and the code verifier, they create a per request secret. And if somebody can intercept that code, he doesn't know the random number, he still cannot turn that code back into tokens, and that's exactly what we want. Okay, as I said, there are a couple of approaches here. We have the system browser, we have private browsers, and so on. If you can, always use the system browser. Then there are a couple of ways how you handle the callback. With custom URI schemes, maybe. My preferred one is what they call claimed HTTPS URIs. It's basically, you've seen that before, maybe when you open a link to, let's say, Amazon, and you have installed the Amazon app on the phone. Instead of opening the browser, it opens the app. And that's because on that link, there is an XML file that is signed with your Apple developer certificate, which says, hey, when you get a link to that, open the Amazon app instead if it is installed on the machine. And that's how you can nicely do the callback from the browser back to your application. Okay. Yeah, that is the saddest part of the talk, I'm sorry. Browser-based applications, okay? Everybody does sparse, right? They're the hotness, I guess. And unfortunately, they are the most hardest to secure type of application. And, the problem is not the SPA or the OAuth or the protocol or whatever. The problem is the browser, right? Ultimately, you're running your application in a shared execution environment with multiple applications that take advantage of the shared state that the browser provides. And there's a whole class of attacks that have the word cross in front, right? For cross-site scripting, cross-site request forgery, because basically one application attacks the other, trying to take advantage of the shared state in the browser, right? So, fundamentally, there are two different ways to secure sparse. Either one is using a credential type that the browser natively understands, like a cookie, for example, or you're using something explicit, which could be an OAuth access token, right? It turns out the cookie has the cross-site request forgery problem, and the access token has the cross-site scripting problem. So you choose which problem you prefer. Yeah? Funnily enough, yeah. So basically, we were asking for this BCP for a long time. Like, can we have an OAuth for web applications BCP just like we have for the native one? And the IETF was tracking their feet for a long time because they knew they kind of opened Pandora's box here, right? Because in the end, it will come out, it's not OAuth, it's the browser. Yeah. So funnily enough, the OAuth for browser-based apps, BCP, is the first OAuth spec I ever read that says, maybe you don't need to use OAuth. Yeah? And their assumption is this. Most applications out there, yeah, they kind of look like this, right? You have a domain, you have a browser front end, you have a back-end API, and they might run on the same site. Okay? So you can secure the communication between the two with cookies. Okay? You still might use an external identity system. That's totally fine. Yeah? You still might have to call some external APIs, but 90% of the communication is same site, right? So you can actually use a cookie and apply some sort of anti-forgery protection to it. Yeah? Now, the BCP makes the assumption that this anti-forgery protection will be same-site cookies, right? That's this newish feature. in browsers. It's called same-site cookies. That basically makes sure that, you know, when you get a cookie from domain 1, that the browser will only send that cookie back to domain 1 if the sender is coming from the same site, okay? A site is, by the way, not an origin, right? An origin is very strict with protocol, DNS name, and port, where the site basically means it's the top-level DNS registrar name, so api.myapp.com and app.myapp.com would be on the same site, so that would work, okay? MVC has anti-forgery protection built in for many, many, many years, actually since day one, I think, yeah? But you have to write code for that. With the same-site cookie, it's more like a browser thing. And you probably also know that the internet will get more secure next week, or broken, as some people call it, when Google decides to change the default value for same-site cookies, right? So up to today, you have to opt into same-site protection. Starting next week, Chrome will basically treat every cookie that does not opt out automatically as a same-site cookie, which means it will not travel across site borders anymore. And if you haven't tested your web app, you should do it very soon. It's going to be 4th of February, okay? So ultimately, the BCP distinguishes between these two scenarios here. One they call JavaScript apps with a backend, and one is called JavaScript apps without a backend, yeah? And to be honest, I'm not really happy about this classification. I think it should be rather a question like, do you want to store your tokens on the server, or do you want to store your tokens on the client, right? If you are running, you know, on the server, you might have a better feeling because they are away from the browser, away from your cross-site scripting attacks, but you're pretty much limited by what cookies can do, and if you're starting to do a lot of cross-site API calls, the cookie won't help you, yeah? But if you're storing them in the browser, you now have, you know, you have to be very careful with cross-site scripting, but it's more flexible, right? So there are different threat models, I guess. And there's no one-size-fits-all answer here. I'm a consultant, I would say it depends, right? But yeah, the real question you have to ask yourself is, you know, am I protected enough against cross-site scripting or not? If you don't have the feeling you can deal with that, maybe storing all of your tokens in the browser, you know, can be problematic. That doesn't mean you are safe from cross-site scripting with both approaches here. I'm just saying it's a different threat model, right? And you have to think about that. Okay. Now, yeah, I mentioned that. Also, you know, think about refresh token storage in browsers, right? There is some guidance here as well. And one of the interesting things is that you can bind your refresh token lifetime to the session lifetime, for example. That might help you. But yeah, again, much more information in these documents that you should read. Now, what's next, right? So I've now gave you an excerpt of these documents, right? And that kind of implies there's more, yeah? So you might think now, that sounds all very, risky and so on. And guess what? There's even like, there are academic research papers that found even more problems, yeah? So the IETF is working on that, right? It turns out, to cut a long story short, the most vulnerable part of OAuth is still the browser, right? I mentioned that. They follow redirects. They show UI, right? That's what makes them powerful and dangerous. And it turns out, in the grand scheme, the biggest problem are the authorized requests, right? The initial requests via the browser front channel to the authorization server. So there are a couple of new specs. Up to even, the work has started on this. Okay? But the IETF is not like the fastest moving company on the planet, as you probably know. So this will take many, many years, right? But in the meantime, what I think is a real possibility is that we're going to have OAuth 2.1 first. So what is 2.1? It's pretty much what I told you about, yeah, like deprecated flows, only do code flow with PKCE, only do client credential flow, some of the other things, and one or two additional specs they are working on right now is, and they say like, hey, if the authorized request is the biggest problem, can we make that better? Okay? And the authorized request, remember, that's the thing where you, via the browser, send all of these parameters to the authorization server, and they can be, tweaked by someone or handcrafted and can probably be used to, to do something that you didn't intend to do. So what about we turn the upper thing into this? What's that? It's clearly a JSON Web Token, right? Because there are 2 dots in it. Yeah, of course. Yeah. And this JSON Web Token basically is the query string just as a JSON Web Token. It's signed, right? Look at that. It has a type. Yeah, so they take their own guidance. So yeah, that's an interesting idea, right? Depending on how big these tokens get, you might have problems with URL length, descriptions, and so on. So there's another spec that sits on top of that, which I think is just a brilliant idea. How about this? You don't do the authorized request at all as the first thing. You first open a back-channel communication to your token server. You authenticate the client, however strong you can authenticate the client, and then on that back channel, the client pushes the authorization request parameters to the server, and then the server stores them and returns that client back a reference to them. Okay, that's all happening on the back channel. So now, on the front channel now, the client will use that reference to make the authorized request. Okay? So no more front channel harmed during the process, so to speak, right? All of the stuff is happening on the back channel. That's what you get on the front channel. No one today, as we know it, can tamper with these things. I'm pretty sure there will be clever people who find different ways of that. But yeah, that's basically where it's heading to, right? Get rid of the front channel, or at least make it much more secure. That spec is called pushed authorization requests. Yeah, and the spec before is called JWT secured authorized requests. Yeah, so they kind of go hand in hand. This one is really, really nice. In Identity Server, we have support for chars today and pars hopefully during that year. Okay, so what's the summary here? Is that depressing? Do you think like, hey, why do I have to use OAuth at all? It seems very insecure, right? So many vulnerabilities and so on. And my answer is yes, you should use OAuth, because you know that the beauty of having a spec and a standard is that you're having a pre-vetted threat model, right? Many people worked on the standards, many people try to break it. Yeah? If you think like, no, I'm going to write my own protocol, then there will be one person who wrote the protocol, and probably only one person who broke it, right? That's you. And I think that's better, yeah? So, you know, to summarize that, some things we can't fix, which is infrastructure stuff. Some things can be easily fixed, right? Get rid of your referrers, get rid of your open redirectors, get rid of your leaking stuff, right? Some threats will be always hard to mitigate, right? If an attacker wants to specifically attack your company, they're gonna analyze how your stuff works and find your weaknesses, right? It's more like an assassination than a drive-by shooting kind of thing, yeah? So, yes, I think still you should use OAuth. I think we have some challenges, I would like to call them, yeah? And we can fix them, but it's getting better every day. So, thank you for that. I always forget we have stickers. If you want a sticker, they are outside. There's a big sign saying Identity Server. You can have stickers there, and besides that, thank you for your time.